Hello students, today we are going to start the next unit, that is 8086 interrupts. In this unit, we will cover various topics such as what are interrupts and its sources, the classifications of interrupts, concept of type number, predefined interrupts, interrupt priorities, interrupt vector table, and the steps involved in servicing an interrupt. So let's begin. Whenever a microprocessor is executing a program and its sequence of operation is broken by a process, then this process is called as an interrupt. So here is the definition for you. Let us focus on the key points. So as you can see, currently the microprocessor is executing a program. For example, suppose you're running a web browser, a Chrome, or even you're typing your document in MS Word or Notepad, whatever it is, and suddenly you insert a pen drive in the USB port of your laptop or desktop, and you would have noticed a slight delay in that. The delay is because currently your microprocessor was executing a program related to your browser or MS Word, and it is getting interrupted by an external process, that is your pen drive. So it needs to give attention to that pen drive, that what it needs. So you can also say that an interrupt is a method or a process by which it seeks the attention of microprocessor. Now whenever it seeks the attention of microprocessor, what does it mean? That it is telling the microprocessor to service it. Servicing means to execute the program related to that process. So this program for an interrupt is called as ISR, or interrupt service routine. Now let us understand this point. So already a microprocessor is executing a program and it is going in serial way, fine. So sequentially it is trying to execute instructions one by one, and this execution of program gets broken by this process, and this process is called as interrupt. Now once the microprocessor goes to this interrupt and it tries to ask, okay, what do you need, the interrupt will say, you need to execute my code. Now please remember here that this interrupt must be of a higher priority as compared to what currently the microprocessor is doing. If it is of a lower priority, then microprocessor may not service it. But if it is of a higher priority, the microprocessor will go there and it will execute its program. Now this program for that interrupt is called as ISR, or interrupt service routine. In some text it is also written as interrupt service subroutine or interrupt subroutine. So usually we call it as ISR, interrupt service routine. This interrupt can be generated by three means. The first one is by an external signal generated by a peripheral device. So when I am talking about peripheral device, it can be both input or output device. The second one is it can be generated by an internal signal. So by an internal signal generated by a special instruction. And the third is it is also an internal signal, but it is due to an exceptional condition which occurs while executing an instruction. So it can be also generated by an exceptional condition while executing an instruction. Now we'll go into the details of each one of these, but for time being, let me just give you an overview of this. So by an external signal generated by a peripheral device or IO device, these type of interrupts are also called as hardware interrupts. And by an internal signal generated by special instructions, so as you would have guessed it, it is also called as a software interrupt. And this interrupt exceptional condition while executing an instruction. So for example, suppose you are doing a mathematical calculation and one of your values in your mathematical instructions gives an expression of 1 by 0. Now 1 by 0 leads to infinity, and this will interrupt the entire execution of your calculation. So this is also an exceptional condition which gets generated while executing that instruction. So this is called as conditional interrupts. Now we will go into the details of each one of them. As discussed before, on encountering an interrupt, the microprocessor stops executing the current program and it goes to the interrupt service routine which has been called by that interrupt. Now before going to the interrupt service routine, the microprocessor also has to ensure that once that ISR has been executed, it will return back to the program where it had left. So the point to be noted here is, first the microprocessor stops the current or stops the execution of current program. All right. Second, it has to go to the ISR of the interrupt. Now before going there, it in between it has to ensure that it needs to return back to this current program after it has executed the ISR of that interrupt. Now how is it done? You know that the program counter or the instruction pointer, it points to the address of the next instruction. So it needs to ensure that this value, it needs to save the instruction pointer as well as the code segment, because 8086 introduces the concept of physical address. Physical address of instruction is made using the content of your code segment and instruction pointer. Fine. And apart from this, the microprocessor also saves the content of flag register, and if necessary any other register will also be involved, so that also is saved onto the stack. Right. And thereafter the ISR execution begins. So this is the normal flow. We'll go into the details of each one of these and we'll try to understand how the stack comes into play and how the data is moved onto the stack, which one goes first, IP, CS or flag, and how the ISR execution begins or how is the address of the ISR takes place. So all these things will be sooner looking into it. Let us understand the various classification of interrupts. So the first way the interrupts can be classified is by hardware and software. So there are hardware interrupts and software interrupts. The second way is the interrupts can also be classified as vectored and non-vectored interrupts. And the third one is the maskable and non-maskable interrupts. So let us try to understand the first one, that is hardware and software interrupts. Hardware, as the name suggests, relates to something which is physical or the physical components of the microprocessor. So hardware interrupts are basically initiated by external hardware. So I can write hardware interrupts are initiated by external hardware, and they give an appropriate signal to the interrupt pins of your 8086. Now if you recollect, your 8051 had 5 different interrupt pins. It was RST 4.5, that is also called as trap, then RST 5.5, 6.5, 7.5 and INTR. But in the case of 8086, it has only 2 interrupt pins. So let us look at the pin diagram of your 8086. So if you can see here, this is the pin diagram of your 8086. This pin, that is pin number 17 and pin number 18, NMI and INTR. These two pins are the hardware pins of your 8086 microprocessor. So any interrupt which is sent on these pins, that is NMI and INTR, they are called as hardware interrupts. So therefore I can write to the interrupt pins of 8086, that is your NMI and INTR. So NMI, you may be aware of, NMI stands for non-maskable interrupt and INTR is called as interrupt request. The second one, which is the software interrupts. So unlike your hardware, software is something which is realizable in form of instructions or instruction codes. These software interrupts are embedded into the program. So software interrupts are embedded into the program. Now 8086 has a special instruction called as INTN. If you recollect, when we were discussing your 8086 instruction set, that time I had left this instruction and I had not discussed about this INTN instruction. So INT stands for interrupt and N stands for the type number. So let me put this in different line. Here int n, the n corresponds to type number of your interrupt. This type number of your interrupt, this value ranges from 0 to 255. So when we are talking about 0 to 255, this number is basically your decimal number. So if you convert this into hexadecimal, it would be 002 FFH. As you can see, it is an 8-bit. So FF takes 8 bits and 00 will also take 8 bit, because 0 to 255 or 256 numbers can be represented by 8-bit binary number or BCD code. INTN is a specific instruction for your software interrupts, whereas for your hardware interrupt there are two special pins, NMI and INTR. You need not to remember the pin number, just the what is the pin description, that is NMI, non-maskable interrupt, and INTR, they are the hardware pins. Now let us move to our next classification. We know that whenever an interrupt is encountered, the microprocessor goes to the ISR and executes the instructions related to that interrupt. Now the microprocessor, before going to the ISR, it needs to know the address. The microprocessor needs to know the address of the ISR, because the ISR is stored in the memory as like all your other programs. So after encountering an interrupt, if the program control transfers to a specific address, then it is called as a vectored interrupt. Now this transfer to a specific address happens automatically in case of a vectored interrupt, and this vectored address is called as the ISR. So I can write, for case of vectored interrupts, after encountering an interrupt or after encountering an interrupt, so the program control gets transferred to a specific address automatically, then it is a vectored interrupt. Now this as specific address points to the ISR. In the case of a non-vectored interrupt, the thing is different. In this case, the microprocessor will not automatically go to that specific address. Rather, what will happen is it will request the interrupting device to provide the address of the ISR, and thereby the interrupting device will supply the address of the ISR. So interrupting device or the process will supply the address of the ISR. Many a times it is said that vectored interrupts are those interrupts where provides a specific address to the ISR, and non-vectored interrupts are those interrupts which does not have any specific address of an ISR. So this is not correct. Because all the ISR will have a specific address. Now the point in the case of vectored interrupt is the microprocessor will have an idea beforehand that okay, this is an interrupt, and for this interrupt, if it is encountered, I need to go to that specific address. Whereas in the case of a non-vectored interrupt, the interrupting device will provide the ISR for that interrupt. It is not that the microprocessor will be knowing beforehand to which address it will be going if it encounters an interrupt. So this is a major difference between vectored interrupt and non-vectored interrupt. In the case of 8086, all the 8086 interrupts are vectored address, and the address is obtained from the vector table, which is called as interrupt vector table. So I can write 8086 interrupts are all vectored ones, and the address of the ISR, the address of the ISR is present in the interrupt vector table, which is also called as IVT, and this interrupt vector table is stored in the first 1 KB of memory space. Now let us stress on this point. So the first 1 KB of memory space, so you know that your 8086, what is the maximum amount of RAM or the memory it can be used with? It is 1 MB of space. So when we are talking about the first 1 KB of memory space, now this memory space can be given by two means. One is your code segment value and another is your instruction pointer value. So the first 1 KB memory space means your code segment will be all zeros and your instruction pointer will be all zeros. Now your 1 KB means how many bits will be used? It will be 10 bits. So the starting address will be defined by your instruction pointer, so it will be all zeros, and the final address of your interrupt vector table will be code segment all zeros, and your instruction pointer will be 03FFH. Now how come we have got this 03FFH? Your F takes 4 bits, another F takes 4 bits, and 0011. So if I write this in binary, I'm just writing this part in binary. Please note, I'm not writing the remaining parts because the rest of them are 0. So if I convert 03FFH in binary, I will get 4 zeros, 0011, 1111, and 1111. So here I am using 10 bits. Now if I am using 10 bits, I will be getting 1K of space, and that is how your address is getting generated. So this is your address of your interrupt vector table, which contains the address of the ISR. Please note, because many a time students get confused in this part, it does not contain the ISR, it contains the address of the ISR for the various interrupts. We'll discuss more about the interrupt vector table in the later point of time, but for time being you can understand that the interrupt vector table is of 1 KB in space, and it contains the various address of the ISR. So its address range is from 0000, that is your code segment, and instruction pointer also is 0, and code segment will still remain 0, and the instruction pointer will end at 03FFH. Now, as we have just now discussed the non-vectored interrupts, let us discuss another concept which is called as INTR cycle, which is interrupt request cycle. Now, just now we have seen the non-vectored interrupt ISR address is provided by the interrupting device. So all these non-vectored interrupts are connected to an INTR pin. An INTR pin is used by the external device to interrupt the microprocessor. Now, when an interrupt request is made through the INTR pin, and if the interrupt is enabled or unmasked, so you remember by which flag bit we can unmask all the interrupt. There is one interrupt flag, the IF flag is called as the interrupt flag, and if the interrupt flag is set to 1, the microprocessor will recognize the interrupt request from the peripheral. So if IF is set to 1, the microprocessor recognizes the interrupts from the peripherals, and if it equals to 0, then the microprocessor will ignore any of the interrupt requests which comes from the peripheral. Now if the interrupt flag is 1 and the microprocessor receives an interrupt through an INTR pin, then the microprocessor will run an INTR cycle, or also it is sometimes called as interrupt acknowledge cycle. So what happens is that we know that INTA bar, okay, I'm not writing the bar here, so please mention the bar. So in the INTA bar signal is called as interrupt acknowledge. So whenever a microprocessor accepts an interrupt, it will send an acknowledge on your interrupt acknowledge pin. So let us first see your interrupt acknowledge pin. Where is that? So if you see here the pin number 24 in minimum mode, this is INTA bar. Okay, so this INTA bar pin is used to send an interrupt acknowledge signal to your peripheral device. It's an output pin. This interrupt acknowledge bar signal is sent twice. So it is interrupt acknowledge is sent twice. Now what is the purpose of sending twice? In the first interrupt acknowledge, when it is sent, so in the first INTA signal, what happens is the processor informs the device that the interrupt is accepted. So the microprocessor informs that the interrupt is accepted, and in the second case, or in the second INTA signal, or whenever the second INTA signal is sent, the microprocessor requests the device to send the type number. So just now we have encountered the word type number. This type number will be sent by the device, and if you recollect, the type number, that is n, is varying from 0 to 255, that is 002 FFH. So this type number will be sent by the interrupting device. So whether it is type 0, type 1, type 2, or type 30, type FF, whatever the type number is, this will be sent by your interrupting device. And as you can see, this is 8 bits. So this data, or the type number, will be sent on the lower order data lines. of your 8086 microprocessor, because your microprocessor 8086 has 16-bit data lines, so this is only 8 bits. So this data, that is the type number, will be received on the lower order data lines. Just to summarize this, what is this INTR or interrupt acknowledge cycle or interrupt request cycle is: the interrupting device sends an interrupt on your INTR pin, and if interrupt flag is set to 1, the microprocessor recognizes the interrupts from the peripherals. Now, once the microprocessor recognizes your INTA or interrupt acknowledge, or sometimes that is why it is called as interrupt acknowledge cycle. So I am writing INTA cycle. So here the interrupt acknowledge is sent twice. In the first case, the microprocessor informs that the interrupt is accepted. So the device is now sure, for whatever reason it has interrupted the microprocessor, now it can proceed. But before proceeding, it has to send its ISR. Now, how will the microprocessor can go to the ISR? For that, it will send the second INTA signal. In this second INTA signal, the microprocessor will tell to the interrupting device to send its type number. This type number ranges from 0 to 255, that is 0 to FFH, and this is sent on the lower order data lines. So I hope you are clear with the interrupt acknowledge cycle. Now let us move to the third classification of your interrupts, which is maskable and non-maskable interrupts. From the name itself, it is quite understandable that maskable interrupts are those interrupts whose request can either be accepted or rejected by the microprocessor, and the interrupts whose request must be accepted by the microprocessor or it cannot be ignored by the microprocessor are called as non-maskable interrupts. So just in brief, I can write maskable interrupts can be accepted or rejected by the microprocessor depending upon critical programs the microprocessor is executing, or it is performing some high priority task, or the interrupt flag is set or reset. So maskable interrupts can be accepted or rejected. The second is the non-maskable interrupts. They must be accepted by your microprocessor. The microprocessor is not having the liberty to reject it. So from the name itself, you can understand the example for your non-maskable interrupts is your NMI, whereas all the hardware interrupts which is initiated through INTR pin are maskable. So I can write the example for your maskable interrupts: all the hardware interrupts which is generated through INTR pin. Now, just now you have seen the case of INTR pin. So whenever any peripheral device interrupts the microprocessor by means of INTR pin, they all are maskable interrupts. So how can they be masked? Now, just now we have seen they can be masked by setting the interrupt flag equals to 0. And the interrupts through NMI pin as well as all your software interrupts are non-maskable. So I can write here, along with NMI, all the software interrupts. So both of these are non-maskable interrupts. Let us focus on one important concept, which is type number. Just now we have gone through the type number, which is from 0 to 255. I would like to spend more time on this type number because the concept of which will be again used in the further numericals or understanding your interrupt vector table. From our discussion up to now, we have understood that a type number is assigned to each interrupt. So type number is assigned to each interrupt. Its values ranges from 0 to 255. So I can write its value ranges from 0 to 255. So there are 256 unique interrupts which can be generated. Now this type number is generated or executed by means of INTN instruction. So this is the software instruction which we are talking about, and these 256 interrupts can be initiated by two ways. The first one, which is your INTN instruction, which we have just now written here this way, and the second way by which it can be done is by your non-vectored interrupts. So how it is done, just now we have seen by your INA or interrupt acknowledge cycle. Now this non-vectored interrupts, the INA cycle is generated by means of your INTA bar, and the non-vectored interrupts are generated by INTR pin. In the first case, it is specified by instruction itself, that is here in the INTN, the N corresponds to whatever it is, whether it is 00 or it can be FF, so the range is 00 to FFH. Whereas in the case of the non-vectored interrupts, the processor runs an INA cycle and the type number is obtained on the lower order data lines. So the lower order data lines come into being, that is D0 to D7. So this data lines are used to obtain the type number. In this video we'll cover up to this much, and in the next video we'll discuss about the various predefined interrupts, which are basically software interrupts. So we'll study your type 0 to type 4 interrupts, and thereafter we'll move towards your interrupt vector table.